Okay, so in this video, I'm gonna revisit a concept that we learned earlier, and that was the concept of the goodness of fit. And previously, we used R squared to measure the goodness of a fit of a model, that is, how much of the variation in the y variable is explained by explanatory variables in the model. So we said higher the R squared, the more variation all of the variables on the right hand side explain in the variation in our dependent variable y. I also said that high R squared does not imply that there is a causal interpretation, and a low R squared doesn't mean that our model is bad. And one caveat of using R squared that we saw earlier was that including more variables on the right hand side increase R squared no matter those variables are related to the dependent variable or not. Instead of using R squared, we can use adjusted R squared to know more about the fit of the model. And again, the value of adjusted R squared is again between 0 and 1. So we put a small bar on R squared to show that it is an adjusted R squared. So what this adjusted R squared does is it imposes a penalty if we add more variables on the right hand side. Adjusted R squared will go up only if the variable that we included in the model has a t-value greater than 1. Right? So sometimes it is advantageous to use adjusted R squared, as I will show you in the next couple of examples. Okay, so here are our two models, and these two models are from MLB dataset, and we are interested in explaining the variation in the log salaries explained by player performance, and these are some of the variables that we could include in the model. And we want to know like which of these two models is a better one, a model with the run batted in a year or a model with home runs per year. So which of these two models give us the best fit? Okay, so here are our two models. If we look at R squared, the R squared for the second model is 0.625, which is less than the R squared from the first model with run batted per year in the model. This implies that model 1, according to R squared, is better than model 2. If we look at the adjusted R squared, we see that the first model, again, it is a little bit better than the second model. In this case, both of the statistics R squared and adjusted R squared are favoring model 1 as compared with the model 2. Okay, so in the next model, we are interested in explaining R&D spendings as a percent of sales based on either log of sales or sales and the square of sales. That is, we can either regress this model on the log of sales, or we can use the quadratic model on sales only without taking the logarithm of it. So the model with the log sales as an explanatory variable, we say that the R squared is 0.06, and when sales along with the square of sales is included in the model, R squared is 0.14, which is not surprising because, as we said earlier, including more variables in the model increases R squared, which is exactly what is happening here. Because we have one more variable in the second model, R squared is higher. So we can look at the adjusted R squared, and remember, adjusted R squared, it imposes a penalty for adding more variables. So in this case, adjusted R squared is 0.03 in the first model and 0.09 for the second model. So we have a preference for this quadratic model without taking the log of sales over the log of sales as the only variable in the model. One thing that we need to be careful about using adjusted R squared is that if we have different dependent variables across models, we cannot compare those models. For example, if we want to explain salary of CEOs as a function of sales and return on equity in our first model, and in the second model we want to explain log of sales as a function of log of sales and rate of equity, We see that in the first model, our dependent variable is salary. In the second model, it is log of salary. And we say that both r squared and adjusted r squared are pretty high for the log model as compared with the first model. Okay, so we may say that the log model is better based on adjusted r squared, but as I said earlier, because both of these models have different functional forms, in the first model the salary is measured in levels, in the second it is measured in the logs. We cannot compare the goodness of these models based on either r squared or adjusted r squared. So the question is, which model should we use? So here we have to go beyond r squared and look at the statistical significance of all of the variables in the model. We see that in the level, both sales and the rate of equity, they are statistically significant at about 10%, but log sales and rate of equity are statistically significant at 1% in the log model. Because this model too has variables, those are more statistically significant, therefore we will probably prefer the second model over the first model. So that's how you use r squared and adjusted r squared to compare different models and compare the goodness of fit across different models. All right, I'll see you in the next video. Bye bye.